Getting better? Right. Okay. Now I am wearing the two-in-one, the earphone and the mic one. So if you cannot hear me, you can actually turn on your mic and then you speak to me. Okay. You can try to speak if you. So if possible now you try to mute your earphone unless you want to talk. Okay. So okay. All right. So I start the recording from now. I think somebody disturb my recording because I already start the recording just now. But now it seems like the recording has stopped. Okay. So by the way, I will restart my presentation once again. Okay. So now we already started recording. Okay. I will repeat one more time. Okay. So for today's lesson, I will continue my discussion. Okay, starting from the DC drive. When you talk about the DC drive, right, you need to make it clear there are two parts about the DC drive that when you talk about the motor itself, right, normally the motor is the body of the motor, like the armature, their winding, their armature resistance, okay, armature inductance kind of things. The component of the DC motor, that one we call as a DC motor. But when you talk about the drive, normally it's referred to the component, the converter circuit that's supplying the voltage to your DC motor. Okay, so we have a different kind of the drive, such as a variable frequency drive for the AC motor. We have a half wave converter. We have a semi converter, full wave converter kind of things. That one is for drive. So the DC motor drive, okay, is relatively simple and cheap. Okay, but DC motor itself is more expensive. How to explain this one? That's why I want you to make it clear. The DC drive here actually is referred to the converter circuit. It's not the motor itself. Yeah, the DC drive actually is referred to uh, the converter circuit that supply the sufficient voltage or current to your DC motor. So for the DC motor, their DC drive is referred to the half wave converter, full bridge converter, and then the semi converter, that kind of thing. That one is referred to the DC drive. The DC drive is relatively simple and cheap compared to the AC motor, because AC motor, the speed is controlled by the frequency and also the pulse. Normally we are referring to the so-called the VFD, then the variable frequency drive, which is much more complicated to be designed compared to the DC motor. However, the DC motor itself is more expensive. The DC motor itself is more expensive compared to the AC motor. For AC motor, they just have two set of winding. One is a rotor, one is a stator. Then that's it. That's enough for the AC motor to work. But for the DC motor, you need to have the armature winding, the commutator. You need to have the brush, and also the permanent magnet, or can be the separately excited winding to make it work. So then this material are costlier, are more expensive compared to the AC motor. That's why they say here, but the DC motor itself is more expensive. So due to the numerous disadvantages of the DC motor, right? Because the DC motor, right, are having much lower efficiency compared to the AC motor, especially in the high power application. That's why nowadays the people are not using the DC motor in the high power application. However, it is still getting very popular, okay, in the low power application, such as the cooling fan for your CPU, for your computer, right? Those cooling, the small power application remain popular because for low power application, the cost of the drive and the motor itself is still economical. Okay, so for servo application, the DC drive is still popular because of the good dynamic response and the easy to control. They are having the very simple speed control. Even though they run at a very low speed, it is very easy to control. Compared to AC motor, it is very hard to control at a low speed condition. I will look at your message. If you cannot hear whatever, please let me know, inform me on this one. Okay, so this slide show you the design of the DC motor. You see, actually the DC motor could be very simple as well. So you have a magnet, okay? The purpose of the magnet, right, is to actually to produce the flux, okay? The flux. I use the drawing pen to demonstrate to you, okay? This is my drawing pen. Too much sensitive. So basically, they will produce the flux, okay, from the motor is from the magnet. So if I'm using the magnet for my DC motor, right, they will generate the flux, okay, the fixed flux. So when the fixed flux, okay, running on the induced on the armature, when you supply the voltage to armature, right, armature is running, so they will generate the rotating flux. So the flux between the armature and the magnet will repel to each other. So since the magnet is a fixed component that cannot be moved, so in this way they will cause the armature to turn. Okay, so this is basically the working principle of the DC motor. And then both sides are connected to the shaft. So the shaft will hold the position, can rotate smoothly. So for the case of the brush DC motor, right, because I'm using the brush actually is a carbon brush, which is one of the very soft material. So after you use your DC motor for a certain period of time, so the DC motor will get very dirty because of the wear and the tear of your uh, wear and tear of your carbon brush. Then also it gets very noisy because of the contact, okay, between the carbon and also the commutator here. So however, the good thing for this motor is that the price for the brush is actually very cheap. Okay, the price is very cheap compared to the Hall effect sensor. So that's why in certain application, if the concern about the dust is not so important, the people still prefer to use the brush DC motor because it's very easy to maintain and very easy to find the replacement. It show you the actual component for your permanent magnet and brush DC motor. So you bear it at the both side, okay, that join them together, and then we have the commutator here and also the brush, right? Just they use a spring to push it to the contact, so they have a firm contact, right? And then because of the DC motor, right, brush DC motor having the problem of the wear and tear issue and also very dirty, so that's why they now slowly brushless DC motor. That's why you can see most of the DC motor used in your CPU, right, your computer, your cooling fan, right, actually are based on the brushless DC motor. That's why they can work at a very silent speed, okay, because there are no contact. Hall effect sensor means they use a sensor as a commutator, okay, to control the energy to supply to the armature. So because it's a contactless architecture, so the operation of the brushless DC motor can be very silent and having the much higher efficiency. Also, the lifespan is longer because there is no wear and tear issue. So advantages of the brushless DC motor is that it has a high efficiency, high torque to the initial ratio. That means I can produce a high torque, okay, by controlling the Hall effect sensor, and greater speed capability, and lower audible noise. This is for sure. Lower noise because there's no brush contact to the armature, and better thermal efficiency. Yeah, it's also it won't generate the heat because of the no contact between the carbon and also the commutator. Lower EMI characteristic as well. So again, this is the comparison between the brush and the brushless DC motor. So the main difference between the two concepts is the way of commutating the motor coil. Okay? So in order for any DC motor to operate, the current to the motor coil must be continuously switched relative to the field magnet. So that means you have to supply the current to the armature. So in the brush type, this is accomplished with a carbon brush, okay, containing a slot commutator cylinder which has each motor coil connected to a corresponding bar of the commutator. The switching continues as the motor rotates. With this arrangement, there are physical limitations to speed and life because of the brush. Okay, because you need to have a direct contact between the brush and the commutator. So when you turn on that time, right? So it's getting very noisy. You can hear the very sharp noise came out from the DC motor. And also in the long run, there'll be a wear and the tear issue. That means they need to have a regular maintenance on your brush DC motor. Compared to the brush motor, the brushless DC motor has no carbon brush to wear out, hence provide the significantly greater life being, now only limited by the bearing wear. Okay, so for the brushless DC motor, the only weakness is on, because if you have a bad bearing past your brushless DC. Okay, for this one, right, I wish to explain the operation of the DC.
Sir, no sound, sir. Hello.
Can you hear me now? Can you hear me?
Yes, yes.
Yes, okay. So I'll continue to demonstrate to you how actually the DC motor work. Okay. So basically, okay. So basically, right, the DC motor can be classified into two family. One is the DC. I think the pen is not good, so I don't want to use the pen. Okay, so I use the pointer. Sorry. Okay, so basically, right, the DC motor can be classified for me into two categories. One is PMDC. Okay, PMDC refer to the permanent magnet DC motor. Then the other one is refer to the separately excited DC motor. Separately. Okay. supposed to use a pen to write, but my pen having the wrong setting. I need to recalibrate later on. Separately excited. Okay. DC. Okay. So for the case of the permanent magnet DC motor, right? The equivalent model for the motor is very simple. So now I have a one piece of the motor, a resistor, and then its equivalent inductor, and also the PED EMF, okay, the rotating part. So this is the VA actually is referred to the armature voltage. They're supplying the voltage into your DC motor. So this is the RA. RA represent the armature resistance, and then this is the LA is armature armature inductance, and also here is referred to the PED EMF in general. So when you turn on the DC motor, so the armature current will be supplied, okay, to your armature. So here, right, for the permanent magnet DC motor, you're using one piece of the magnet. Okay, this is the magnet to generate the fixed flux to your motor. Okay, so the flux, right, that generate from the motor, okay, is given by the phi, okay, phi F actually, field flux actually. So and normally for the magnet there will be a field constant. So the flux that be induced on the armature now is actually given by the formula K. Okay, K is referred to the field constant. Field constant multiply with the field flux. This will give you uh, the flux constant, okay, that apply on the armature. So when you look at the formula itself, right, actually the formula can be very simple. During the instantaneous, that means during the build-up condition, your VA, right, VA is actually equal to IA RA plus the inductor side is omega. Omega is a rotating speed of the motor, and then it's a L A plus the back EMF, the EA in general. So when you apply the voltage, right, so the interaction between the armature and the magnet will cause the motor, the shaft, this is the shaft, right, to turn. Okay, the turn at a certain speed. Omega is referred to speed with the torque being generated. Okay, so this VA, right, this formula is referred to the instantaneous formula. But when the motor is running at the steady stage, right? At the steady stage, your inductor value, there's no changes on the on the voltage, so the complex component will be terminated, so that your VA now can be rewritten to be this formula equal to IA RA and then plus the back EMF. I use the capital letter is used to represent their steady state operation. Okay, and then for the case of the DC motor, right, the torque, right, torque is proportional to the current, so it will be equal to K, and then the flux from the field, and then multiply with the armature current. So this is actually the formula for the torque that been generated from the DC motor. So this one actually is referred to the flux constant. If I'm using the permanent magnet DC motor, right? So I have a fixed flux. But later on, if I replace the magnet with the separately excited DC motor, then the flux will be adjustable. Okay, this will be seen with the case number 2 later on. Okay, and then the second one is about the PED EMF. The PED EMF, right, is actually is proportional to the speed of the motor. So they will become K flux and then multiply with the speed. This will cause the motor to operate at this speed. Okay, so later on, so when you sub this formula into the formula, this will give you IA RA then plus the feed flux, and then multiply with the speed. So by this, we will be able to derive the formula for the speed. Yeah. So the speed actually is equal to the terminal voltage, right, minus with the armature current and the armature resistor divided by the fixed flux. So this will give you the basic derivation about the DC motor formula. So from here you can see, this is the formula for the speed of the DC motor. The speed is controlled by your input voltage, VA. Okay, but at the same time, we will notice that, right, your motor is also affected by the armature current. In other words, they will follow this kind of profile. Okay, any kind of the AC motor or DC motor will follow this kind of profile. So here is referred to torque. Here is referred to the speed. Okay, can you explain to me, right, why when I trying to increase the torque, right, I increase the torque, the speed will getting slower and slower. It happened to be the same like when you drive your car, right? You drive your car going uphill. When you're going uphill, so you press your pedal. You press your pedal more. But when you press the pedal more, but the speed is getting less. So what is the reason behind? Okay, the reason is because if I want to going uphill that time, so the torque has to be higher, because to generate the higher torque to move uphill. So when I want to move uphill, if I want to increase the torque, I need to increase the current. Okay, this is for sure. The current has to be increased. So when I increase the current, that means that it will generate the higher the internal loss. See, the higher the current, when the current multiply with the white armature resistor, so they will cause the internal loss. That means your motor will be heated up very fast, and then overall your speed will get in slower. Okay, it move at slower, but with a higher torque. That's why they will have this kind of the profile for the DC motor. Okay, so make sure you understand. So in case I ask you why, okay, the motor is running at the lower speed when if I want to increase the torque. So this is the reason. You can explain through their formula. So this is about the separately excited DC, about the permanent magnet DC motor. Okay, so now I want to continue with the second part, which is about the DC motor, but with this time is separately excited. Okay, for the separately excited DC motor, the case is slightly different. Sorry. Okay, for the separately excited DC motor, so basically they will have the same equivalent circuit, resistor, inductor, and also the back EMF side like this. Then here the motor will turn. Okay, this is, for example, this is the plate, your fan, for example. So it will turn at a specific speed and also with the torque given. Okay, just like I forgot to mention, when you talk about the speed, right? The speed normally the people will mention in terms of the RPM, for example, right? It's 100 RPM. RPM represent the round, the revolution, how many turn per minute. So they use the RPM. But when you want to use this speed for the calculation, right, you have to convert the RPM into the radian per second, because RPM is not our SI unit. So you have to convert them into the SI unit, radian per second, for the calculation purpose. So the conversion method is like this, very simple. It's 100, okay, multiplied with the pi divided by 30. Okay, so this will give you radian per second. So this is very important conversion. When you want to use this formula for calculation, for whatever, you need to convert the RPM into the radian per second form. Okay, please aware about this one. Okay, now come back to your separately excited DC motor. So this is still the same. Here is the RA, the armature resistance. This is the LA. So here will be the PED EMF. Okay, so here is the supply voltage. Okay, supply voltage like this, VA. So if I'm using the separate excited DC motor, that means I have an external winding. Okay, the external winding that supplied by the separate force, normally we call it as a field voltage. Okay, when I turn on this external winding, so when the voltage fall across the field resistor, then they will be able to generate the field current. So it's IF. So the IF is very important because the torque all are controlled by the field current. So the field current here actually is referred to the VF over the RF in general. Okay, I hope you are clear with that one. Okay, so now that means my flux now, if I using the magnet that time, right, I have a fixed flux. So if I'm using the separately excited DC motor, so now I have a adjustable flux because my flux now is controlled by the formula K and IF now. Okay, KIF. That means this will give me the so-called adjustable flux into my armature. So let's say if I want to increase the torque of the motor, right? Actually, I can control the field voltage, or I can control the armature voltage to control my field current and also the armature current, so that I can control the torque. So this is the actually advantages of the separately excited DC motor because they have a adjustable torque control and also the speed control by adjusting your field winding. Okay, so come back to the general formula again. So your VA is equal to the IA, same thing, RA plus, okay, the complex part, omega L, and then plus the PED EMF, okay, like this. So when your motor is running at the steady stage, means when they achieve the equilibrium, right? So your complex component will become 0. So finally your formula of the output voltage will become IA RA, and then plus the PED EMF. The PED EMF here is referred to the K, okay, and IA, okay, and also the speed. Okay, the omega here is represent the speed of your motor now in terms of the radian per second. Okay, so just how you can compare, right? For the case of the permanent magnet DC motor, I have a fixed flux. So now if I replace the magnet with the separately excited this winding, so now I have an adjustable field flux in this case. So in this overall, my speed can be further controlled using this formula VA minus, okay, IA A divided by the K. So that means I have a different way to control my my speed of the motor. So this is about the speed of the motor, and then the second one is the torque. Okay, for the previous permanent magnet DC motor, the flux is a fixed one. So, but then if I'm replaced with the separately excited coil, right, the winding, now the torque can have a much better control, which is equal to IF and then multiply with the IA. That means I have a better torque control, okay, compared to the permanent magnet DC motor just now. I can adjust the field current and also the armature current to so that my motor can run at a different torque capability. So when you have a torque, right, so they run at the motor. Remember that the motor is connected to the bearing, okay, the bearing at the both sides of the bearing. So there are few losses on the shaft here. The loss can be referred to the bearing loss, can be referred to the damping loss, and also can be referred to the load torque loss kind of things. So the actual output torque that generate from here actually is referred to this formula. Okay, the torque, right, minus the loss. For example, B is a damper, B d delta dt. Okay, this is the damper loss because you are connected to the bearing. So this is a bearing loss. Then if you are able to overcome the bearing loss, then you will generate the motion. So it's a J d square delta then dt square. So this is actually the formula about how to calculate the torque and how they can operate according to the speed and also the torque requirement. Okay, so this is what we have about the DC motor. Okay, from here you can see, class, there are two components which is very important for you to understand. Under this topic, right, about the motor drive, there are two parts that I want you to really understand. One is on the so-called the DC motor itself. Okay, DC motor itself. The motor itself is referred to the PMDC. Okay, PMDC, and also the separately excited. Okay, separately excited. Separately excited DC motor. This one is referred to DC motor. We have two different motor. They have about the same formula on how to determine the speed and also the torque of the particular motor. But when you're talking about the drive, okay, this one is very important. When we're talking about the drive, what's the meaning of drive here? Actually, the drive here is referred to the component, or can say it's an input component that provide the input voltage to the field voltage and also the armature voltage. So this actually is controlled by the drive. Okay, this is what I mentioned just now about the converter. We have different kind of the converter that can provide, okay, the sufficient armature voltage and also the field voltage into your DC motor. Okay, so the drive here, that's why the drive here can be classified into a few different types. Okay, the most straightforward one is referred to the what they call, let me check this, referred to half wave. Half wave converter. Okay, half wave converter. And then the second one is referred to the semi, okay, semi converter. And the third one is referred to the full converter. Okay, so this is what we're going to learn in the next lesson, right? About different kind of the converter that can use to provide different voltage, okay, the sufficient voltage into the field and also to the armature by controlling their fire angle. Okay, so you can take a look, okay, on the next slide. Okay, this is the one I explained just now, exactly the same. So this is the simple design for the DC motor. So see, in the DC motor, the field flux is established by the stator. Stator actually is referred to the magnet and also referred to the separately excited winding lah. Okay, for the permanent magnet motor, the flux is a constant because we use a magnet. Magnet having the fixed flux, you cannot change the flux already. For the DC motor with the field winding, okay, the field winding means the separately excited winding, right? The flux is controlled by the field current. So they have this formula KIF. Okay, it's same like what I mentioned. See, it's a KIF. If I use a magnet, then this will be the fixed one. Okay, right. So the torque is proportional to the the field flux and also the armature current. If I'm using the permanent magnet, so the flux is a fixed one. Okay, so and then this is the PED EMF. Okay, the PED EMF is proportional to the speed and also the field flux. Okay, this is a formula if I'm using the permanent magnet. Then if you run in practical, a controllable voltage source V is applied to the armature terminal to establish the, the armature current. Okay, by the voltage. This one actually is referred to armature voltage. They use the VT as terminal voltage or VA. So normally I will use the VA, okay, to represent the armature voltage. When they supply the voltage, so they will be able to generate the current, armature current. So this one is their equivalent equation that represent the DC motor. So at the steady stage, the current is a constant. So there will be dIdt will be equal to 0. So by this, you'll be able to get the formula that represent this DC motor at the steady stage. When I write in the capital letter, that means the motor is running at the steady stage. Yeah? EA is referred to the PED EMF. This is the KE. Actually, KE actually is referred to this one. Okay, KE psi F actually is whole thing actually divided with the speed. Now this is the operation of your DC motor equivalent circuit. Yeah. So this is the PED EMF. The one that running is the armature is turning, right? So they have two brushes. The brush will have a direct contact with commutator. Then it will cause the shaft to turn. When the shaft is turning, so of course there are some bearing loss. Okay, the BL is referred to the bearing loss, and then the TWL is referred to the working load torque. When I want to turn my load, so I will experience some repelling force. Or that one is referred to the working load torque lah. Okay, so the actual output torque is this electromagnetic torque is referred to the so-called the developed torque. Okay, normally I also can represent this with the TD. Yeah, TD is referred to the developed torque. Developed torque, you minus the working load torque minus the bearing loss, then it will cause the motor to turn. So this is the turning of the shaft. Okay, so this formula you will learn about a lot about this formula in the next trimester about the control system. Okay, at the moment, you can skip about it first. Okay, so this is what I mentioned just now. Yeah, why if you run at the higher torque condition, the speed is become slower. Okay, it's because it's related to this formula. If I want to increase the torque is proportional to the current. Okay, if I want to increase the current, then it will cause the internal loss. So this is referred to internal loss. That's why if you actually try to overload the DC motor, right? Let's say, for example, you use your small car to drive uphill to Genting Highland, to Cameron Highland, you will notice that the car will run at a lower speed even though you press the pedal a lot. And at the same time, you'll notice that the water will get overheated. That's why a lot of the car will stop at the roadside because of the water is boiling, water is overheated, engine is overheated. There's a reason because when you are work under the overload condition, okay, a lot of the internal loss will happen that will cause the heat being generated. So this is actually proportional to heat as well. Higher loss means there'll be a higher heat generation. Then if the heat is too much, will not be able to cool down, then your water will get boiled and then your car become no power. Then you have to stop your car at the roadside until the water being cooled down again. So this is the behavior of the motor. Okay. And then for the case of the separately excited DC motor, okay, the formula are about the same. The difference now is that now I replace the magnet, right? I replace the magnet with the external field winding. Okay, so we have the separate supplier. The supply can come from the same source. Okay, then it connect to the here. It can directly bypass. Okay, directly loop the supply voltage from the amateur voltage to the fuel supply. There will be one way. Another way is that there were different separately converter to control the field current and also the amateur current. For example, here, right, at the input at the amateur side, I can use the full converter method to control the amateur current. But then at the field side, I can use the semi-converter method to control the field current. So this is depend on how you want to configure the motor. Okay, there are many configuration available in this. So we have the half wave converter, we have the semi converter, we have a full converter, also we have a dual converter and kind of this. So there are many kind of the converter available, which I will explain in more detail in our next lesson. So for the separate excited DC motor, they have a adjustable field flux, adjustable field flux. So in general, this is the equivalent circuit. You apply the field voltage across the field resistance. Okay, then you will generate the field current. Then they will induce on the armature. So they cause it to generate the torque and also generate the motion. Okay, no need. The formula. This is the instantaneous field voltage. Instantaneous means during the build out or during the changes of the stage of the condition. It means during the building that time, right, they don't achieve the steady stage yet. So they need to consider the changes on the inductor. Okay. But when you are able to achieve the stability, so the rest formula are the same. This EG is referred to PED EMF is see now is the PED EMF, right, is proportional to the KIF. KIF is referred to the field flux, is controllable by control the field current. Then this is the speed, okay, the speed of the motor shaft turning. Then the torque also the same. The torque now is have a extra control. Okay, the torque is proportional to the DD here represent the developed torque. They mean the torque that developed from here, from the motor itself, the developed torque. It's not referred to the output torque, because the developed torque, the output torque, right, actually is referred to the developed torque minus the losses. Okay, the loss may be happen at your bearing at the load side. Okay, so you need to consider the loss before you can find out your actual output torque. Okay, so the torque is proportional to the field current and also the armature current in general. So at the steady stage, they were following. This is the formula for the output torque. Okay, so at the steady stage, your terminal voltage, right, the armature voltage is equal to IARA from this formula, and also from the PED EMF, EG. EG is equal to K IF and omega. So by this, we will get the formula used to represent the speed control of your separately excited DC motor. Okay, the difference between the separately excited DC motor versus the permanent magnet is that there will be one extra, okay, field current control only. Okay, for the case of the permanent magnet, they will have a fixed flux. But for the case of the separately excited DC motor, there will be extra field current control. Okay, if the internal resistor is very small, normally it's very small. I think it's about 1 ohm, 2 ohms only. Typically, it's very small. Okay, if the power is very high, then this internal resistor sometimes can be ignored. Okay, so that means the speed of the motor can be roughly estimated by using this formula. Okay, this formula can be used to calculate, to estimate the speed of your motor, but not so accurate one. to be more precise, we still need to consider the full formula. Okay, and then the power can be determined by two formula. One is by the developed torque multiplied with the speed, or you can use this formula also. You can use the EA, the back EMF multiplied with the current. Okay, yeah, you have two different ways to calculate the developed torque. Okay, so the developed torque will need to overcome. This actually refer to the resistance, the obstacle. I will explain more detail about this if you study the control system in next semester. Obstacle. Obstacle is due to the losses, due to the bearing. This is due to the bearing. This is due to the spring effect, spring effect of the load. Because when I want to turn the load, there may be some inertia, there may be some load torque, okay, working load torque. Okay, and then this is the motion, okay, the rotating of your shaft. So this is the motion. So when I generate the torque must be overcome the obstacle in order for me to generate the motion. This is my explanation about the mechanical system. Okay, torque generated minus the obstacle, it will cause the shaft to move. If you're not able to overcome the obstacle, then the motion will be zero. So this is the very simple behavior about the torque, okay, torque behavior. So this formula is very simple. Okay, I already explained this formula, inside your tutorial, because this is one of the tutorial that I discussed. Okay, it's the same tutorial. So before this, I also need to mention when you want to do the calculation, right, you use the formula of the speed. Okay, speed normally is expressed in terms of the RPM. All right, in terms of RPM, which is referred to revolution per minute or round per minute or circle per minute. It's up to you how to express it. But normally when you want to use this speed for the calculation, right? Normally we don't use RPM. For this case, I use RPM because it's okay, because during the calculation it will terminate by itself. So it's okay for me to use the RPM. But in the more standard, you need to convert the RPM into the radian per second. Okay, you can try at home. You can try this example. For example, this tutorial example, you replace the omega, right, 1/4 with the radian per second. You convert you convert the radian per second, then you try to calculate the value. At the end, you get the answer in terms of the radian per second. Then if you convert back into the RPM, you will get back the same formula. Okay, in certain calculation, you need to convert to the radian per second. Only for this example, we don't need to use the radian per second, because internally it can serve by itself. So they get back the same answer. Okay. So next time in the exam, whatever, right? So please convert to the radian per second before you can use the speed for your calculation purpose. Okay, so you can see from here, right? The torque, okay, the speed is proportional to the voltage. Okay, and then the torque is proportional to the current. This is about the torque. This is about the speed. This happens to all kind of motor, okay? It's a DC motor or AC motor. This is the true for all kind of motor. Okay, the next one is the one I want to emphasize about the DC motor drive. Okay, DC motor drive here can be a half wave converter, can be the semi converter, and can be the dual converter configuration. Okay, what you need to do is that you need to controlling their fire angle. See, control the fire angle, so that it can control the amount of the energy of the voltage that been generated to the amateur voltage of the DC motor. So this one I will explain in more detail in our next 2-hour lesson. Okay, so I will stop my discussion. Do you have any question? Ask. Paul, do you have any question to ask? If no question, then I will stop my for our try to complete chapter 5.